I actually haven't been to math science in the last 2 decades, so this has been great, and the meeting so far has been tremendously illuminating for me. So I have a strange title. So to understand the title, the soft capricious matter part of it, let's look at this micrograph of something which happens to be cornstarch suspension. So the kinds of systems that I have been interested in understanding the collective behavior of are collections of particles like this. So the problem this kind of system poses is that if let me just make you look at just these two particles. Even if I take these two specific particles, imagine they're suspended in a fluid and the fluid is making them move, rotate, etc. At this point in time when the snapshot is taken, the particles are touching at this point and they have some forces acting on each other. As soon as they move or rotate, those forces are going to change. And this is just two particles. Every particle, because these are macroscopic particles, they have, I used to have a scale bar here. So these are more than micron sized particles, like 10, 20 micron sized particles. Because they're macroscopic, these particles have attributes that we normally don't think of when we are thinking of collections of particles like atoms and molecules. So each particle is distinct, they have a shape, they have a surface. So the interactions between them are hugely complicated. And one can try and model them in terms of forces acting between them by putting in some kind of friction coefficient. But I actually don't even know how to model friction between things. One can go to like microscopic structures and say, the surface looks like this, so this is what the interaction looks like. So maybe we start to think of these systems in a slightly different way. And so that's the perspective that you'll hear from me today. But before I talk about, before I go into that, this work has been in collaboration with a bunch of people, Shubhra Bhattacharya at ICTS, Kabir Ramola at TCIS Hyderabad, Itai Cohen at Cornell, Jeff Morris, who is at City College, and Xiaoming Mao, Michigan, Emanuela Delgado at Georgetown. So I have benefited tremendously from the collaborations, and you'll hear some parts of, not all of the work is what you're going to hear about, some of it. Currently, the people at Brandeis who've been contributing to this work is this amazing undergraduate who just graduated, Albert Countryman, and Konaya, who some of you know, was at ICTS as a graduate student with me. Mike Dion was a graduate student. Jishnu was a graduate student. Now he's back in India. Okay, so I want to understand the collective behavior of particles like this, and the reason for me calling these noisy interactions is precisely what I sort of tried to say in words, that you don't know what the interactions are. And this is something Jean-Philippe Bouchot many years ago said, that there's a kind of noise in these kinds of systems, which is not just statistical noise. We don't know the interactions well, so what do we do with them? So one aspect of the collective behavior that is very important to understand in these systems is the rigidity to flow transition, the jamming, unjamming transition. So when are they rigid? Why do they form a solid? Like these cornstarch suspensions don't even have any attractive interaction between the particles. So why would they even form a solid? When do they flow? When do they stop flowing? So the basic question that motivates us is, how do we construct statistical field theories for systems like this, sort of close to their rigidity transition? So I'm not going to talk about all aspects of their collective behavior, but close to the rigidity transition. So as I've already said, and maybe it wasn't obvious, but these systems, they're large enough that there's no Brownian motion. Thermal thermal noise is completely irrelevant for these systems. So non-Brownian, noisy interactions. So the approach that we have taken, sort of the conceit of that approach is that these systems navigate a constraint landscape. So instead of a free energy landscape, it's a constraint landscape. And the particular constraints that we are thinking about are those of mechanical equilibrium. So these things, the suspensions, even if they're flowing, instantaneously the force and torque balances are satisfied. They might be flowing due to external forces, and also these systems will not do anything until I drive them with some external force. So if I put a bunch of cornstarch particles on this stage or put sand grains or whatever, they don't move by themselves. There's no, unless I do something to them, they stay in one particular configuration. So the exploration of phase space is also only through driving. So we start from this notion that can we understand the collective behavior of these systems by saying that systems, we shouldn't think of interactions, but we should think of the collective behavior as emerging from them satisfying the constraints, some set of constraints. And then the other part of what we are thinking in constructing a theoretical framework is the force-bearing networks that can support external stresses and in response to them either flow or stay rigid, emerge in response to external forces. There is no solid, there's no force-bearing network present if I don't have any external stresses. So then what I'm going to show you in this talk today is that these constraints can lead to conserved quantities. This is not a new notion. It's very well known in some parts of physics. We haven't used it maybe so much in this kind of non-equilibrium soft matter physics. So again, this is a non-equilibrium system. You've probably been hearing over the course of the last 2 days that one of the challenges of non-equilibrium systems is what is the distribution. So once you have a conserved quantity, then there is a natural, in these systems at least, there's a natural ensemble that emerges, which is a kind of a microcanonical ensemble satisfying this constraint. And this, for people in the granular glassy community, is the Edwards ensemble. Here you'll see it emerging from a much more basic concept than we have usually discussed in the community. So that, I think, was my last thing. So a natural ensemble emerges from this conservation principle. So before I go into talking about what is this theory theoretical framework that we have, let me give you some examples of the kinds of systems that I'm thinking about. So where I started from are granular systems. So this on the left-hand side, and someone said this, I don't remember who, I think it was Sunil, who said he didn't want to use the word jammed because he would get shouted down. I use a very specific definition of jammed or jamming, and that was introduced in this paper in 1998 by Cates, Whitmar, Bouchot, and Claudin. Jammed systems are whose solidity emerges from the applied stress itself. So there is no solid without applied stress. So that immediately tells me that there is no stress-free solid ever, unlike the normal kinds of things that we talk about. There is no stress-free solid. And the real space network is therefore not predetermined. The real space network emerges from the stresses you put on the solid. And so there is, unlike standard elasticity theory, there's no constitutive relation between stress and strain because I don't even know how to define strain, and I'll get more into that, because there's no stress-free reference state. So there are multiple pre-stress states that are all equivalent in some way. So to show you some examples of pre-stress states, these are images taken with photoelastic beads from Bob Berenger's lab way back. And what you're seeing here is a two-dimensional bunch of particles. The particles are very difficult to see, but it's a dense assembly of particles. You can think of it as a kind of a sand pile, but it's just a rectangular sand pile. There are boundaries at the left and right. And what you're seeing is, because these are photoelastic, the light areas is where the forces are large, and the dark areas are where the forces are very, very small. So as you can imagine, if I just look at this is under gravity. Of course, there's more mass at the bottom, and it sort of looks like the Q model that Satya came up with many, many years ago. So you can come up with models like this. So this is this well-known notion, or a notion which has a kind of mysticism associated with it, called force chains. And what this image is taking this system and then putting a small external force on top of it. And this is what happens after that. And these two images at the bottom is just the response itself. So I subtract A from B. So you see this classic propagation under gravity of the forces. And what I will convince you by the end of the talk is it actually comes very naturally once you think of the system in terms of this conserved quantities and the constraints. So natural response and correlation functions have this structure. On the right here, I'm showing you a system that I'm not going to talk about at all in this, but it sort of, again, is very illustrative of the stress-induced jammed structures. And this is actually experiments in the cornstarch suspension, the image of which I showed you before. And what you're seeing here is a phase diagram. This is the packing fraction, so the fraction of suspended particles in just normal liquid. I think this is glycerol and cornstarch. And this is an implied shear stress. So what you're seeing here, and ignore the DST for now, but they undergo this interesting phenomena of shear thickening. But if you look at this region, the red region is where the suspension is jammed, it cannot flow. In this whole blue region, it can flow. So now, if I am sitting up here, let's say, at high stresses, if I reduce the stress at a given density, it will start flowing, which is sort of weird if you think in terms of elastic systems, because normally we think you have a system which is rigid at zero shear stress, and then if you applied a lot of shear stress, it will yield or fail. This is sort of the opposite that you need the stress to keep it jammed. And the reason I was asking Ludo about whether the tau p is relevant or not is that in this system, we have now shown clearly that this sort of zero shear stress jamming point is singular. The stress is a relevant perturbation because it introduces friction between particles. So this is a frictionless jamming point, and as soon as I go to a non-zero stress, there is some friction, and we have actually now shown that that's a relevant perturbation. But that's a story that I'm not going to talk about today. But this is a flowing to jamming to flowing unjammed transition that you see around here. Okay, there are many more examples that I can think about. I wanted to quickly show this one. Wanted to come up with examples where people actually have thought about the system in terms of constraint satisfaction. And this is tissue remodeling. Actually, this is a collaboration between experimentalists and theorists, Boris Scheinman's group at Santa Barbara. And they come from this, so the tissue flows. And they're asking the question of how does this tissue flow? It's so dense. And their, again, conceit or their approach is to say, it's an active solid that's undergoing plasticity, plastic flow, but the plastic flow is completely determined by the constraints of force balance. So whatever geometrical rearrangement is taking place here, where the cells rearrange, is actually just to satisfy the constraints of force balance. And they have actually come up with a complete dynamical theory to explain this kind of tissue remodeling using this force balance idea. One more sort of active system, which is people have actually, in the active matter community, haven't thought about so much, is solidification due to active stresses. So this is from my former colleague and student, Zvonimir Dojic's lab in Santa Barbara. And what they have is a passive network, it doesn't matter what it is, and an active network of fibers, long fibers. And this active network, when they turn on the activity, a very weakly cross-linked passive network, which wasn't a solid, can actually become a solid. So again, that solid doesn't exist without these active stresses. Okay. So much for giving you examples. Oh no, I have one more. Sorry, because I'm going to talk about this. So this is gels. And gels have this property that they become solid at very low concentrations because there's actually attractive interactions between the particles. So my collaborator and friend, Emanuela Delgado, studies these gels. And what they noticed is the kind of network that forms can depend not only just the density, but also the protocol they use to create these. So these two gels are exactly at the same density, but this one was a faster quench rate than this one. And these viscoelastic properties change with that. So what I'm going to show you by the end of the talk is that there is an interesting connection between the continuum theory that we will talk about, mostly talk about today, and the kind of networks that form here. So this is a rigid floppy transition, again, the same kind of. So the other thing I need for you guys to sort of be aware of and think through is that these systems, I'm saying they satisfy constraints, and there are lots of constraints. They're highly constrained, and I haven't told you yet what the constraints are. So the constraints, let's say in the gels, are at every particle is in force and torque balance. So there's local constraints. At every contact point, there's force and torque balance. And then there are some, in the gels case, there are some internal stresses that develop due to the fluid, which I also don't know, right? So at the boundaries of these dense regions, there are forces. So it's a highly constrained system. There is constraints at every point, but it's also a highly degenerate system. And what do I mean by that? I'm saying this is not the only configuration that I can get by cooling. If I do it again, I'll get another configuration. In the previous example of the photoelastic beads, if I repeat the experiment, I'll get a different configuration. So we have this highly constrained by highly degenerate set of states. So I need to come up with some ensemble. I need to come up with some kind of way of thinking about how to ensemble average, how to think of these systems. So it's a very different perspective in thinking about rigidity or what's a solid compared to the traditional paradigm of elasticity theory or rigidity. So the way we are going to think about it is it's a highly constrained system. There are lots of configurations. When do, as an ensemble, these configurations behave as a solid? Or in the flowing system, I'm exploring phase space through the flow. When do they stop flowing and they become jammed? The traditional paradigm of rigidity comes from broken symmetry. Right? So even though classical theory of elasticity is very old, we know now the rigidity comes from breaking a continuous translational symmetry. So crystals break symmetry, crystals have a particular pattern that they prefer. So that's how, and they have phonons which are Goldstone modes. So that's where rigidity comes from. even thinking about it macroscopically from a continuum perspective, what is really fundamental in the standard way of thinking about rigidity is strain. So I have some reference structure, which is, let's say, a square here. I have distorted it, and the distortion I represent by a strain tensor. The strain tensor is constructed from displacement fields, which are vectors from, like every point here gets displaced. So that's this displacement field. So strain is fundamental. And strain is fundamental and has this structure. That tells me, this might be a weird notation, but think of it as a double curl and a curl, of the strain tensor has to be 0. So this is something that's known in elasticity theory and is known as the compatibility relation. So strain is fundamental, it has these properties, and then there's a notion of stress, which is derived. So stress is derived by taking the derivative of a free energy with respect to the strain tensor, and momentum conservation, of course, applies, and momentum conservation in this case, in these cases, is just the divergence of the stress tensor is whatever the external force is. There is no del T of momentum here. And then if in linear elasticity theory, we say linear response, so there's an elastic modulus that connects the stress to the strain. So if I now want to determine the stress state of this system, so I want to know the field, the stress field everywhere, I have enough equations. I have this equation. So in 2 dimensions, my stress tensor has 3 independent components because the stress tensor is symmetric. So I have 2 equations here. But then I have to use this equation. I have to use this equation in combination with that equation, and that gives me enough equations to solve for the stress state. This is not something we explicitly talk about sometimes because we just assume elasticity theory, but I need this. I need this. Without that, I cannot solve for the stress state of the system. So for the rest of the talk, what I'm going to do is ask, can I come up with a set of equations which lets me solve for the stress state of the system when I have no notion of strain? So I cannot connect to strain. Is there a stress-only formulation of rigidity or elasticity theory? That's going to be the bulk of my talk. This one? So this one, in 2 dimensions, it's just enough. In 3 dimensions, you can take any of them. It's overdetermined. But if you don't have this, then you absolutely don't have enough. And you'll see that in the way we come up with it we map a different theory onto the stress problem. In that theory also, there's this overdetermination problem. Okay, so the next thing I think I'm going to skip, just wanted to say that the plasticity in normal elasticity comes from violation of this condition. So in crystals, when we talk about defects like disclonations and dislocations, this is non-zero. And in amorphous systems, there has been a search for similar defects by, again, asking when is this compatibility relation violated. Okay, so the next slide I think I can skip, but basically what I'm now looking for is, can I have a stress-only formulation of elasticity theory? Can I come up with a stress compatibility relation without relying on strain, ever? So to do this, I need to introduce this idea that constraints can give rise to conservation laws. And to do that, I'm going to use a model. So you should turn off basically trying to understand the microscopics of the model that I'm going to just flash before you in the next slide. The microscopics comes from a very different system, but the notion that's illustrated in there will be very important for us. So what I'm trying to do here is get you used to this idea that constraints can give rise to conservation laws of a kind that we are used to in other parts of physics, but not so much in soft matter physics. So this system, what I have drawn here, for people who know this system, maybe so, these are some representations of the ground states of the triangularizing antiferromagnet, but that's irrelevant for us. Let's say what I have is a system where I have this honeycomb lattice, and on each bond of this lattice, I can either have two arrows pointing, let's say here, pointing up, and one arrow pointing outwards. So two arrows coming inwards into this vertex, two arrows going outwards. And I have the constraint that at every vertex, this has to add up to 0. So if two are coming in, two have to go out. I cannot put two here. Then that violates the constraints. But I can put them in any order here. But at every vertex, I have to satisfy this constraint. And so this is one possible state that I can have. This is another possible state that I can have, which is actually ordered. All of these two arrows are in the vertical direction. One thing that comes from this constraint, which might not be so obvious, is if I now add up, let's say the total, if I think of this as a current or a flux of an E field, an electric field, that's how we're going to think about it. If I think about what's the flux of the E field in the vertical direction, so if I look at this row, there's 4 going up, 2 coming down, so there's 2 net. Every row has to have 2. I cannot change it. So there's a local conservation that propagates through the system. So then you can understand that the only way I can change this number 2 is by doing something at the boundary. Or I can violate the constraint. But if I'm not allowed to violate the constraint, I cannot change this. So in this one, I have 2. In this one, you have the maximal flux. So every maximal vertical flux. And so the number of configurations that satisfy this total flux condition, in addition to this local constraint that every configuration has to have, depends on what is this total vertical flux. So here I can only have 3, right? I only have 1 if I say the vertical flux has to be this. So the way to construct continuum theories for models like this has been explored. I don't want to say explored to death, but explored heavily in the community of classical spin liquids. And what you do is you say, okay, this field, let's say these lattice sort of E fields whose fluxes have to add up to 0, that tells me that I have a Gauss's law. I have a divergence of E is equal to 0 at every point. So the continuum theory is just built upon this Gauss's law. And if I just want to look at the static configuration, the ensemble properties of the static systems, then I have to rewrite down a free energy, which looks exactly like the electrostatic Lagrangian with the E square. And there's a stiffness here, which depends on which flux sector I'm in. So the stiffness depends on whether I'm here or here. And there's a natural ensemble associated with it, which is that all states that satisfy the constraints are equally likely. And the reason is there is nothing else that distinguishes them. All of these configurations should be treated in exactly the same way. How many minutes do I have? 10? 5 minutes in question? I have only 10 minutes left? Okay. Okay, so I'm going to go quickly. Okay, so I'm going to quickly, this is just going to be a mapping. So now I'm going to look at jammed solids, let's say the granular solids, and I'm going to think of it in this kind of paradigm, that's a constraint satisfaction problem, and that these solids don't exist unless I have external forces. So let's imagine I have external forces which are just pressure, and then there are contact forces that develop between grains inside this. this system now satisfies constraints, which is force and torque balance, right, at every point. So think of this as analogous to satisfying that divergence of E equal to 0 in my previous system. So this is just divergence of this coarse grain will give me a divergence of sigma equal to 0. This will give me sigma is symmetric, but this is another conservation law. So the question is, and I'm going to skip quickly to that. So in the previous problem, I had charge is conserved, right? I had Gauss's law, divergence of E is 0, so charge is conserved. In this system that I'm thinking about, I have two conserved quantities. And the question is there an E&M-like framework which has two such conserved quantities? Is there a gauge theory which has two such conserved quantities? If there is, then I'm basically done. And then I'm going to just show you results. So the hard work was done for us in 2018, and this is how all of this, well, the story started long ago when Silke was a graduate student with me, but the closure to this theory came because I was talking at ICTS and Shubro told me about this theory. So this theory, and you can ignore this side of it, but there are, in 2018 or even earlier, people had been trying to develop these tensor gauge theories, which are U1 gauge theories, just like a normal E&M. But here, the E and B fields are symmetric tensors. They are not higher form gauge theories for the experts in the audience. They're symmetric tensors. And there can be two kinds of Gauss's law for these symmetric tensors. We're going to ignore this one. This is the one with the vector charge. So very simply then, what do I have? If I just simply mapped the E tensor to my stress tensor and the charges, which are here vectors, to my forces, I have the divergence of sigma equal to force or divergence of sigma equal to 0, Gauss's law. So we can just go ahead and develop this. This tensor gauge theory has these four Maxwell's equations. If I look just at the electrostatic version of it, which is just the left-hand side, then what do I get? I get divergence of E as the force, and I get this compatibility equation because in the static, the right-hand side is 0. There's no current and there's no B field. So I get a compatibility relation for the stress. There is no strain involved in here. And then we just have to do a little more work, which I'm going to so just to make it clear, then this theory actually has these two conservation laws, which are these two conservation laws for me. And the reason this has been interesting in the spin liquid community is these two conservation laws highly restrict the way charges propagate. So because I'm running out of time, I'm quickly going to go into that. Yes? It can be, in this theory, you can have magnetic monopoles because it's not a real E&M theory. I haven't talked about the magnetic field at all because it doesn't show up unless I think about dynamics, or equivalently, I can think of the stress as E or B. Nothing is coupled unless I have dynamics. And then the magnetic monopole would be the force. Yeah, let's forget about that. Yeah. Okay, so I'm just going to say this. We had to do a little bit more work, but that's not so important. We had to go to a dielectric version of this electrostatic framework. But basically, this is the rigidity framework that we end up with. So the divergence of the stress tensor is F. The stress tensor is like an electric displacement field, like if you have a polarizable medium. And the E field is like the normal E field. And I don't know how to measure that. So the stress is this, but this is the E field. And that's the one that satisfies a compatibility relation. And now there is a relation, if I think of this as a linear dielectric, then there's a relation between stress and this is not strain. These phi's are not displacement fields, they are just gauge potentials because my E field satisfies this condition. So it's completely the reason for the compatibility relation is not because I derive something from a displacement field, but because in the static limit, I have to satisfy this condition. So basically, that's the story. I'm just going to quickly show you 5 minutes into questions. I'm already into questions? Yes, okay. So this is quick. So these are just, this is 2020, 2022, but these are predictions of the theory about stress correlations. So it's a field theory. It predicts stress correlations given some coupling constants, but we can extract the elastic moduli by fitting numerical or experimental measured correlations to the theory. So that's something that we've done. But I wanted to quickly show you what force chains are. Force chains, so these three configurations, these three pictures that you see are actually exactly the same configuration. And you would see in this one, I'm seeing force chains in the horizontal, force chains in the vertical, force chains along the diagonal. What these experimentalists, Jie Zhang and Inchio, did was they colored the grains by the x component of the stress. This is colored by the yy component, and this is colored by the xy component. So what we see as force chains is a property of the stress correlations, and the stress correlations are highly anisotropic. So the longitudinal correlations and the transverse correlations, so the longitudinal correlations are positive and extend, and they are power law. The transverse correlations are also power law, but they're negative. So this is what's basically going on in force chains. Okay, so that's the end of the story, and I know that, so I just wanted to show you we can calculate the response, and the same thing happens. I'm going to completely skip all of the gels that I wanted to talk about and go to my summary. Okay, so let me just put up my summary and then thank you all.
So can you explain what the gauge theory, gauge field is? So how to detect the gauge field in your, which you introduce phi I, phi j. So you shouldn't connect such field with an observable. Like
how do I connect a potential to an observable?
Yeah, but
I don't
any
know.
effect, can be connected to the original vector potential, which is
so this is not a vector potential. This is
I know.
That is static potential.
Yeah, I know that. So you should explore the connection between the real field and your gauge field.
Real field and a real gauge field. I don't know how to do that, but I can tell you that if you say that I am looking at two configurations, and I will just say my potential is 0 in this configuration, and then you ask what the displacements are of the particles from this configuration to that configuration, that will show up as your electrostatic potential. So basically what we are saying is there's no notion of a unique reference state. So if I now ensemble average, there's no notion of a displacement field. Yeah. But I can always fix the gauge for one. I can just say the electrostatic potential is 0 for this configuration, and then I can measure potential differences. I cannot measure the absolute potential. And there's no Aharonov-Bohm effect that we have figured out yet.
Yeah.
That's a, yeah.
So recently I heard a talk by Anil Lemaitre who he talked about stress correlation.
Can I just say something, and Anil will agree to this? He has a mathematical formalism.
Right.
So
but maybe the rest of the people...
if I say divergence of stress is 0, then the stress tensor can be written in terms of a potential, which is known as the Airy stress function. So if you know the Airy stress function correlations, you can figure out all of the stress correlations. This is what Anil does in a very complicated way, because he says if I measure one correlation function, I can measure the others. But by measuring that one stress correlation function, he is figuring out what the Airy stress function correlation is. So if I know the Airy stress function correlations, I can work everything else out. It's writing the stress in terms of a potential. He doesn't have a theory for why the Airy stress functions have to have that correlation. But I have a Lagrangian. I can give you all of the correlations of I write the Lagrangian in terms of a potential. There is no unknown in here.
So here you have two conservation laws, right? So and you are using the Edwardson symbol where all the things are equally likely basically. But in general, if you have, let's say you have n conservation laws,
Yes.
then
Yes.
this GG or something, generalized Gibbs symbol that you use one Lagrange particular for each of the conservation laws.
Yes.
So how does, if one does, is it necessary to do it here or not necessary?
You mean to how do I incorporate the two conservation laws? Is this what you're?
Conservation laws, you can.
Oh, are you saying more?
In many ways. So one. Generalized Gibbs.
No. Right. But here there is a more basic thing. Is I have a Gauss's law. I have charge conservation. So basically everything is incorporated in the fact that I have vector charges, and these vector charges have to be conserved, and because the fields are symmetric, then the charge angular momentum also needs to be conserved.
Okay,
so it's a more basic charge, there's a physical sort of charge conservation embedded in there. So that's it comes very naturally. Yeah. Yes, it's microcanonical because if I say that everything is just determined by constraints, then every configuration that satisfies those constraints are equally likely. And the theory only emerges after I do that ensemble average. The continuum theory is an ensemble average theory.
Okay, perhaps we can move on to the next speaker. We're a little bit late.
There's one.
Okay, well, Shiva,
Thank you.
we move.
My question is if there is an intuition behind the stress compatibility condition, because when we talk about the strain compatibility, we talk that the displacement field, it should be sufficiently smooth and there should be no discontinuity in the displacement.
Right. So it's a very different intuition here, and I didn't get to talk about it. So if you violate the stress compatibility relation in normal elasticity, that's a defect. The only way I can violate the stress compatibility relation here is by introducing a B field, which means I immediately have dynamics. So that's actually a very appealing picture to me, that in these kinds of solids, if I violate compatibility, the system will immediately flow. There is no way of supporting a static defect structure, unlike the strain compatibility. So that's not an intuition, that's math, but that's the difference.